Okay, I want to continue our discussion of electronic configuration and bonding, and we're going to move on to Lewis structures. So basically, the Lewis structures in an atom are the electrons in the highest energy level. So we can define the valence shell as the outermost electron shell of an atom. So for carbon, there's six electrons total. Two of the electrons are in the inner shell, and then there's 4 in the valence shell. So there's two valence electrons in the 2s orbitals of carbon atom, and then there's 2 more in the p orbitals, the 2p orbitals of the carbon atom. Okay. And these valence electrons that are involved in the formation of chemical bonds. So valence electrons are all about the chemistry of atoms. Okay, we can represent, first of all, we can represent Lewis structures of atoms, and we can represent Lewis structures of molecules. Okay, so. Okay, so to represent the valence shell electrons of an atom, we can draw each electron as a dot with the symbol for that element. So for example, here's the valence electron configurations for different groups of elements. Okay, we'll start with hydrogen, the simplest element. Now hydrogen has 1 electron in the 1s orbital, so it has 1 valence electron. If you add another electron to the orbital, you have 2 valence electrons in the 1s orbital. So helium, this is the Lewis configuration, the Lewis structure for a helium atom. It has a completely filled shell of electrons, okay, because it's in the n = 1 level. And remember, there's only 2 elements in two elements in the n = 1, the lowest energy level. So that's why there's only 2 elements in the first row of the periodic table. Now, if we go to the element with atomic number 3, there's 2 valence electrons in the 1s shell, the lowest energy shell. We don't lose that we don't lose those electrons, but we're adding an electron in the lithium atom to the 3rd energy level. So we add 1 electron and to the 3rd energy level, and there's 1 electron in, so there's 1 valence electron. If we move on to beryllium, if we add a 2nd valence electron to the 2s orbital, we get an electronic Lewis structure for beryllium shown here. Now we filled up the s orbitals in the n = 2, the 2nd main energy level. Now we have to move on to p orbitals. So what we have to do at this point is we have to add we keep the 2 electrons in the 2s orbital, and then we add 1 electron to the 2p orbitals, and now we get a configuration of boron. Carbon now has 4 valence electrons, boron 3 valence electrons. So we add another electron, a 2nd electron to the p or to 2p orbitals, and we have the Lewis structure for carbon. So we keep doing this. Nitrogen 5 valence electrons. This is the Lewis structure. Oxygen 6 valence electrons, and then we go fluorine, which contains 7 valence electrons. Now, once we get, remember, we can only hold up to 6 electrons in the p orbitals. So when we get to neon, we fill up and there's a maximum of 8 electrons in the n = 2 level, or the 2nd main energy level. So we fill up that level with 8 valence electrons. The same thing now, if we move on to the 3rd main energy level, and we start filling that up, we fill the 3s orbitals first, then we fill the 3p orbitals, till we finally get 8 electrons in the 3p orbitals, and we have an octet of electron. We have the maximum number of valence electrons in the 3p, or in the n = 3 level. So Now, this configuration or this trend only holds for the representative elements. Okay, so we're talking about, when we talk about valence electrons, we're talking about the configurations in all of the energy levels, main energy levels. When we talk about valence electrons, we're talking about only s and p orbitals, electrons in s and p orbitals. We're not talking about the d orbitals. Okay, so for the transition metals, you have these d orbitals, but we're only going to worry about electrons in the s and p orbitals. Okay, in particular, what I want to point out is that elements within the same group of the periodic table have the same number of valence electrons. So elements in group 1A all have one valence electron. And these elements are called the alkali metals. If you have two valence electrons, you're in group 2A, and this corresponds to the alkaline earth metals. Now, if you keep moving on, you have a group 7A. These are called the halogens, and they all have 7 valence electrons. In group 8A, well, helium's the exception. It only has two valence electrons because it only has, in level 1, you can only have an s orbital, and s orbitals can only contain 2 electrons. Whereas when you go to level 2, you can add p orbitals. So p orbitals can hold up to 6, and you have the 2 in the s orbitals. So you have a total of 8 valence electrons, and that's the basis for the octet rule. You have a maximum number of electrons in a maximum number of valence electrons. So the atom gains some stability by having that filled valence shell. Okay, so this is the Lewis structures for the individual atoms, and then atoms in group 8A are called the noble gases. And I'd like to point out too that the number of valence electrons is simply the group number. So group 5A, nitrogen has 5 valence electrons. Group 6A, oxygen 6. So if you want to know the number of valence electrons, you can always look at the group number. Okay, so now, what is a bond? Okay, well, we just talked about this. A bond holds each atom together, but what goes into a bond formation is forming the electronic configuration of the nearest noble gas, okay, in the periodic table. So if an atom gains an electron to achieve a noble gas configuration, it acquires a negative, overall net negative charge, because the number of protons or the atomic number of that atom doesn't change. But if it gains extra electrons, it has more a net charge of negative. It has more electrons and protons, so that's an overall net negative charge. Whereas if an atom loses an electron, it becomes a cation. It becomes positively charged. It now has more. It loses electrons in the neutral atom, so now it becomes an ion, a positively charged ion. It keeps the same atomic number. So what an ionic bond is the formation of an electrostatic attraction between a negatively and positively charged ion. And so this buildup of opposite charged ions over 3 dimensions leads to the formation of salt crystals. This is why ionic compounds like sodium chloride form crystals. One of the reasons. Covalent bonds now result from the sharing of electrons. So you can achieve the noble gas configuration with 2 atoms by sharing of the electrons between them. So we can now classify bonds as ionic, polar covalent, or non-polar covalent. So there's two types of covalent bonds. There's polar covalent and non-polar covalent. And that's based on something called electronegativity. Electronegativity is the proclivity or the attraction of an electron by an atom in a shared bond. Okay, and there's a certain number scale called the Pauling scale associated with electronegativity. Now, nonmetals, especially when you go towards the upper part of the periodic table, those tend to be the most electronegative. So those like to acquire electrons. So when you have a bond, say, between something that's very electronegative and something that's more not as electronegative, it's a positive, the electrons in those bonds are going to be pushed more towards the fluorine atom, because the fluorine atom has a higher affinity, so to speak, for the electrons. So, so in terms of like the periodic table, the metals tend to have a low electronegativity. They like to give up their electrons to become cations. Okay, it's easier for them to achieve noble gas configuration by giving up electrons, whereas non-metals like fluorine, they need to gain an electron just to move over to the configuration, the electron configuration of the nearest noble gas. Where something like lithium here, if it gives up an electron, it can achieve the stable noble gas configuration of helium. Okay, so here in full glory is the Pauling, this periodic table, where each element is the electronegativity according to this Pauling scale is shown on the different atoms. So you can see fluorine has the highest electronegativity, and cesium, the lower left of the periodic table, has the lowest electronegativity. And the electronegativity increases from in a given row from metals, the left side to the right side. And then as you go from the bottom of the periodic table to the upper part, you get an increase in the electronegativity, okay? So there's certain trends here in electronegativity. All right, so how do we classify chemical bonds by electronegativity? Well, what you do is you look at the difference between the electronegativity of the two atoms in the bond. So for example, if you wanted to determine, like if you had a bond between hydrogen and fluorine, so the electronegativity difference for those two is going to be 1.9, okay? So if you look at the difference and you look at this chart, electronegativity of 0.5 to 1.9 is considered a polar covalent bond, okay? So if it's less than 5, then it's deemed non-polar. So something like diatomic hydrogen, if you have the same atom in both ends of the bond, they have the same electronegativity, so they pull the electron in they share the electron symmetrically, so there's no proclivity for one hydrogen atom in a hydrogen molecule to take the electron versus another. So we call that a non-covalent polar bond. If you look at a carbon-hydrogen bond, the electronegativity difference is also less than 0.5, so we consider a carbon-hydrogen bond a non-polar covalent bond. Whereas if you have something greater than 1.9, that's considered an ionic bond, okay? So here's an example of how you form ionic bonds. So if you have sodium, say metallic sodium, which is very reactive, it has one valence electron in its 3s orbital, and you have fluorine now, elemental fluorine. It has 5 electrons in its 5 valence electrons. So if sodium gives up its 1 valence electron, it achieves the noble gas configuration of neon, which is 1 row above. The sodium ion would have this configuration up to 2p6. That's the configuration of neon. Whereas if you give the 1s electron to the 2p, to the valence shell of fluorine, 1 more valence electron in the p, you would achieve the noble gas configuration of neon. So, so what you end up with is a positively charged cation, sodium cation, and a negatively charged fluoride anion. So you form like this ionic compound, sodium fluoride, and the 2 ions attract each other and form over distance with lots of these interactions building up, these favorable electrostatic interactions, you form an ionic solid, okay? And in organic chemistry, we actually show, this is, when we have an electron transfer, we show where the electron is going by a single-headed arrow. So this is a transfer of a single electron. It goes from the sodium atom to the fluorine atom. So we denote electron transfers in organic chemistry by these curved arrows. Now, if you have, you know, the difference in electronegativity is 0.5. When you have like electronegativity less than 1.9, for example, then it's considered a covalent bond. But of course, you have these polar and nonpolar covalent bonds. So both of these are covalent, but depending upon the difference in electronegativity, one type of bond is polar covalent and the other's nonpolar covalent. So you see, if you have hydrogen, okay, a hydrogen atom, if two hydrogen atoms, each with one valence electrons, share it with each other to form a bond, okay, each hydrogen atom has 2 electrons, so it has the configuration of its nearest noble gas, helium, and that's what you want to achieve by electron transfer or sharing. Now, the sharing of an electron pair between 2 atoms in a bond is denoted by this single line, okay? Now, when you form this bond, you give off heat. It becomes more of a stable, by sharing electrons, you delocalize the charge on the electron over 2 positively charged protons, 2 positive hydrogen atoms, and that's a more stable, you're delocalizing the electron, a negative charge, and that's a more favorable energetically. So that's kind of a common thing in organic chemistry too, is delocalization of electron charge over the molecule, okay? All right, so let's look at polar covalent bonds in a little more detail. We have a certain nomenclature to describe this polarity in the bond. So a polar bond means that one atom in the bond has an excess of electrons over another atom, and it's the more electronegative atom in that bond that pulls the electrons toward it. So as a consequence, the more electronegative atom acquires a buildup of electrical charge, negative electrical charge, more electrons, versus the element in the bond with the atom with the lower electronegativity. So we give we put a symbol on the atom with the higher electronegativity as a delta minus, and that on the atom with the lower electronegativity as delta plus. And you can see that here. And then we draw an arrow. When we have an arrow with a vertical line at the beginning, that indicates a dipole moment, okay, a polarity in the bond. Okay, and you have a polarity in the bond because you have a slight difference of charge. You have partial charges separated across a distance. That's called a dipole moment. So if you take a molecule like hydrogen chloride, which has chlorine is quite compared with hydrogen, chlorine is more electronegative, and the bond is considered polar covalent. You can also show a colored figure here, an electrostatic potential map, where the red indicates regions of higher, larger electron density, and blue regions of lower electron density. So you see most of the electron density is sequestered over the chlorine atom versus the hydrogen atom that has a lower electron density. Okay, so now we're going to learn to draw Lewis structures. We drew Lewis structures of atoms. Now we want to draw Lewis structures of molecules. So this involves a number of steps. So what we have to first do is we have to determine the total number of valence electrons in the molecular ion. And that we can determine from the formula, okay? And we also have to know which atoms are bonded to what, the arrangement of atoms in the molecule. Which atoms are bonded to what? That's what we need to know. That's often the most difficult part of drawing these Lewis structures, okay? So if you have two atoms, okay, it's obvious the arrangement. It's one atom is bonded to another. You have one bond between two atoms. Three atoms, you can have three possibilities. If you have three different atoms, you can have three possibilities of which atom is the central atom. Okay, so as the number of atoms goes up in a molecule, the possible arrangement of atoms increases very rapidly. Okay, so you need to know the arrangement to draw the Lewis structure. Then you connect these. Once you know the arrangement, you connect them by a single line, which denotes a bond. Okay, which denotes two electrons in a bond. Then what you do is you arrange the remaining electrons around the other atoms, so each atom satisfies the octet rule. Okay, so what you do is you show the bonding electrons as these single lines, and non-bonding electrons are going to be shown as pairs of dots. The non-bonding electrons are also called lone pairs. And then you can see that atoms can share either one pair of electrons or two electrons to form a single bond. They can share two pairs of electrons or four electrons to form double bonds, or three pairs of electrons to form triple bonds. And the reason they do that, they share multiple bonds, it's all about achieving the octet rule, okay? They may have to form double bonds because you may be limited to get to the, to satisfy the octet rule, because you may be limited in the number of valence electrons that you put into the molecule, okay? So if you're limited in that case, you have to share more than two electrons to achieve the octet rule. So here's an example of some Lewis structures of, for example, water. If we count the number of valence electrons in water, there's one valence electron for each hydrogen. So there's one valence electron from the hydrogen, one from this hydrogen, two valence electrons. Oxygen has 6 valence electrons, an oxygen atom. So we have 2 plus 6, 8 valence electrons. Well, we already put in 2 here for this bond, 2 here for this OH bond. So we put in 4 valence out of 8 of those valence electrons, and we put the remaining 4 as pairs of dots. There's 2 lone pairs. We call these lone pairs, okay? Hydrogen chloride, 8 valence electrons, 1 from the hydrogen atom and 7 from the chlorine. We put in 1 bond, so we're left over with 6 valence electrons. We don't put the electrons over hydrogen because it already has 2 electrons. It satisfies the duet rule. It's got the configuration of helium already just by having that single bond. So hydrogen rarely, if at all, forms multiple bonds. Okay, it only usually just forms 1 single bond. And chlorine, well, then you put the remaining 6 electrons in chlorine and you put them in pairs. So you have 3 lone pair electrons around the chlorine atom. Now methane, CH4, you have 4 from the carbon, they have 4 valence electrons, and then 4 from each hydrogen. So you have a total of 8. You connect the lines and you end up with, you account for all the 8 valence electrons in the single bond. So this is you don't have to put in any more excess electrons because you accounted for all of them by forming 4 single bonds with the carbon. And by the way, in organic chemistry, carbon-hydrogen compounds, carbons usually are the central atoms, and then hydrogens are usually at the periphery. Ammonia, if you count 8, you have 8 valence electrons for ammonia, a total of 8. So there's 2 in each bond. Okay, this is the connectivity. So you have 6 accounted for by the formation of these 3 single bonds, but then you have to put in 2 more on the nitrogen to get to the 8 valence electrons. So what we're saying is that you have lone pair. This is the lone pair of electrons on the nitrogen atom. Now, in some cases, like I said, you have to share more than one pair of electrons. An example, ethylene. So we have 12 valence electrons in ethylene. Okay, in order to satisfy the octet rule, given this number of valence electrons, what we have to do is we have to share 2 pairs of electrons with, between the 2 carbons. Now, for formaldehyde, we have to share 2 pairs of electrons with an oxygen, and we need to do that in order to satisfy the octet rule on the carbon and the oxygen. Okay, so we'll get to some examples of drawing these Lewis structures in a moment. Okay, so there's some general rules about neutral molecules, and here's hydrogen, like I said, usually has just 1 bond. Carbon has 4 bonds, but usually doesn't have lone pairs. Nitrogen has 3 bonds and 1 unshared pair of electrons. Oxygen, 2 bonds and 2 unshared pairs or lone pairs. And halogens like chlorine, fluorine, fluoride, they usually have 1 bond, and they have 3 lone pairs or unshared pairs of electrons. Okay, so we also have a concept of a formal charge. Now, the formal charge is the charge on a single atom, that atom in a molecule. And if you have a polyatomic ion that has covalent bonds, but has a net overall excess or deficiency of valence electrons, then we have to figure out, well, where is that charge localized? So this is where this concept of a formal charge comes in. And to determine the formal charge of an atom, what you do is you assign each atom all of its unshared non-bonding electrons and 1/2 of its shared bonding electrons. Then you compare that number with the number of valence electrons in the neutral atom. Okay, and if the number is less that you calculate is less than the number of valence electrons in the unbound atom or the neutral atom, then that atom has a formal positive charge. If the number is greater, it has a negative formal charge. So there's a formula here for determining the formal charge. You just take the number of valence electrons in the neutral unbonded atom, or in other words, the group number for that atom. So for example, this number here for carbon would be 4, oxygen, you put a 6 here. Then what you do is you look at the lone pairs you count all the lone pairs of electrons. So if you have 2 lone pairs, you'd have 4. So you'd put a 4 here. Then you look at all the bonds. And each bond, what you do is you take 1/2 of all the shared electrons. Okay, so if you have a double bond, and so you'd have, if you have a double bond, you have 4, a total of 4 bonded electrons, and you take 1/2 of that, and you'd have 2 electrons. Okay, and I'm going to show you. So let's go back to like this slide here, and I could show you how that. Well, these are all neutral molecules, but let's see if we can determine the formal charge. If there's another way to do it without really going to the formula, a simple way, what you can do is just, you can count by the bonds. So look at, so you take the number of bonded electron, you take the number of like non-bonded electrons in carbon. In this case, it would be 0. There's no lone pairs. Okay, they're all bonded electrons. So you count the number of bonded electrons, 1, 2, 3, 4, 5, 6, 7, 8. You count the double bond as 4 electrons. So you take 1/2 that number, which is 4, and then you subtract that from the valence electrons in a neutral carbon atom. 4 minus 4 is 0. So the formal charge on the carbon in this compound is 0. All right. So let's at this point, let's do some of these examples, and we'll draw some Lewis structures for some of these. Okay, so we're going to now, we're going to draw some, the Lewis structures for some molecules. So as an example, we're going to take, the first one is going to be the ammonium ion. So let's draw the Lewis structure for the ammonium ion. So what we could do is we're going to draw, we're going to come over here and we're going to draw NH4 plus. Okay. So first, let's determine the molecular skeleton. So hydrogens usually have to go on the periphery because they can't form more than 2 bonds. So they can't bond with each other. It's because if they bonded like this, that would not be good, because then this hydrogen would have 4 valence electrons, 2 from each bond, and we can't have that because we can only have up to 2 electrons for hydrogen, a hydrogen atom, okay, to satisfy its the duet rule. Okay, so let's what we have is we have those 4 bonds. So then this is the connectivity. So what is the number of valence electrons? The number of valence electrons is 5 for the nitrogen, plus 4, there's 4 hydrogen atoms, 1 valence electron each. And that gives us a total of 9 valence electrons. But then we have a plus charge. So we're deficient in one of these 9 electrons, so we have to do a subtraction, and we end up with 8 valence electrons. So if the ion is positively charged, we have to subtract 1 from the total number of valence electrons. Likewise, if the ion is negatively charged, we have to add the number of electrons that we add to make that charge. So if we had a 2 minus for a -2 charge, we'd have to add a +2 to whatever number we calculate based upon the sum of the valence electrons for the neutral atoms in that compound. So we have to put in 8 valence electrons. So how do we do that? Well, let's go back here. Okay, and we go back here, and we have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in each single bond. So basically, we've accounted for all the electrons, but we're not done yet, because we want to know where the plus charge, which atom it's on. And the hydrogen atoms, if we use the formula, formal charge of the hydrogens is equal to 1 for the neutral minus, there's no lone pair, so how many bonds does it have? Well, it has 1 bond each hydrogen, and there's 2 electrons, so there's 1/2 times 2 bonding electrons, so that's 0. So each hydrogen has the same bond with the same nitrogen, so each hydrogen has a formal charge of 0. So what about the nitrogen now? So the nitrogen has 5, a neutral nitrogen has 5 valence electrons, minus the number of lone pairs, which is 0. And what we have here is we have 1, 2, 3, 4, 5, we have 8 valence electrons, 2 in each bond, but we have, or 8 bonding electrons, I should say, but we have to times that by 1/2 because they're bonding electrons, and that's 5 minus 4, which is equal to +1. So the +1 charge, in essence, is over the nitrogen. The nitrogen atom has a plus formal charge. Okay, so the positive charge in this compound is localized over the nitrogen atom. Let's do another example here. So I'm going to, so let's go to the next one, the next example. Let's do the carbon monoxide. Let's see how that one works. Okay, so let me go here. So we're going to do carbon monoxide. So let's see if I can. Okay, so it's all set to go. So carbon monoxide. That's the formula. It's clear that we're going to have at least one bond connecting the carbon and the oxygen. And then where do we put the rest of the electrons? That's what the Lewis structure is all about. So the number of valence electrons is equal to, how do we do this? It's equal to 4 for the carbon plus 6 for the oxygen. So that gives us a total of 10 valence electrons, all right? But then we already have 2 accounted for here, so we're left over. We have to put a remaining 8 valence electrons as lone pairs around the carbon and the oxygen. Okay, so what we're going to do is we're going to draw. Oh, why that S here? Okay, so we're going to draw carbon and oxygen like this, and we have to put in the 8. So let's start doing that. We'll start with the oxygen because that's usually the more electronegative. So we put the electrons starting with the more electronegative one. 1, 2, 3, 4, 5, 6. And then we have an octet here already. So then we put the remaining 2 on the carbon. Now we have to see if each atom satisfies the octet rule. Yeah, the oxygen does 1, 2, 3, 4, 5, 6, 7, 8. So we're okay on the oxygen. The carbon's only has 1, 2, 3, 4. We only have 4 valence electrons for the carbon, and we need 4 more to satisfy the octet rule. So how do you do that? Well, you do that by forming multiple bonds, these double and triple bonds. Double or triple. So what we do, if we take a lone pair from the oxygen and form a bond, use it to form a covalent bond, another single bond with the oxygen, then we'll have this scenario here. Now the oxygen still has 8 valence electrons. There's 4 from the double bond, but then there's 2 lone pairs, and that still gives us 8. The carbon, it has the 2 lone pairs. It has 2 here, and it has 4 from each of the bonds in the double bonds. So it has 6 valence electrons, but that doesn't quite satisfy the octet rule. Now you ask, why do you use the oxygen lone pair versus the carbon? Well, if you use the carbon lone pair, there's no lone pairs left over on the carbon, and you still wouldn't be able to satisfy the octet rule. So oxygen has enough lone pairs that it can donate and still satisfy the octet. The octet rule still satisfied. So we leave the lone pairs on the carbon alone. If we bring in another lone pair here, then we can form something that looks like this. Okay, and it's neutral. It's a neutral molecule. So the next question is the formal charge on the carbon and the oxygen atom. Well, to do that, the easy way to you don't need the formula. You can use sort of intuition. Remember, you count each electron in a lone pair as 1 electron, and then you count each of the 2 electrons in a bond you just consider one of them. So 1 electron here for the carbon, 2 electrons for the carbon, 3 electrons for the carbon, 4 electrons, 5 electrons. Okay, so you have 5 electrons if you count 1 electron for each single bond or each bond, and then then each lone pair electron. So there's 5, but neutral carbon atom has 4 valence electrons. So you have one more electron than you do in the neutral atom. So we assign a formal charge of -1 to the carbon. Now let's do the same trick for the oxygen. We have 1, 2, 3 here, 4, 5. Okay, so we have 5 electrons, valence electrons in the molecule, but the neutral oxygen atom has 6. So we have less electrons in oxygen in this compound than we do in the neutral carbon atom. So we have a deficiency of 1 electron. So then we put a plus here. You don't need the -1. You can just say, why can't I get the eraser? You can just say minus here. Okay, so so this is the Lewis structure of carbon monoxide with the formal charges. Okay, so that's very interesting. What if we did? Let's play. Well, we'll save that for later. Let's move on to another example. Let's just see why the okay. So let me go back to this, see what the next one is. Let's do NO2 plus. Okay, so I'm going to go show the whiteboard. Okay, so we're going to do the next one. We're going to do is okay, so I got to. Let's see. Okay, NO2 plus. Okay, so it turns out that the molecular skeleton, if you have an electronegative oxygens and in one less electronegative atom like nitrogen, then usually the oxygens go on the periphery. So this is the molecular skeleton of the NO2. Oh no, we don't want. We just want two oxygens. All right. Let's see. All right. So what's the number of valence electrons? The total valence electrons is 5 for the nitrogen, plus 2 times 6 for the oxygen, plus we have a plus charge, so we have to actually subtract 1. So 17 minus 1, we have 16 valence electrons to fill in. So if we start doing that, we'll put them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what I did is no, actually that's not right, because I forgot to do something important. And what we forgot to do was subtract what we already have in the single bonds. So we actually have to subtract the 2 electrons in each single bond. So really we have to put in 12 electrons, valence electrons. So if we go nitrogen, oxygen, oxygen, so we have to put in 12. Let me erase, let me make this clear. So nitrogen, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 valence electrons here. Now, the important point here is, let's see, the oxygens actually, they both satisfy the octet rule, right? It's the nitrogen that we're in trouble, because it only has 4 valence electrons. So we need 4 more. So the logical step would be to bring in 1 lone pair from one oxygen and the other pair from the other oxygen. That would be a more symmetrical line of reasoning. Then we can also put it 2 from one oxygen, but that would give you a Lewis structure, which is not as energetically favorable as doing it this way. But we're going to get to resonant. We can get 2 resonant structures. So if we put, so what we can do is we can do like this for this oxygen, then we'd form a double bond for this oxygen here. And so we'd end up with something like this. And now the oxygen satisfy the octet rule, and the nitrogen now 1, 2, 3, 4, 5, 6, 7, 8. The nitrogen has 8 electrons by sharing 2 double bonds. Now, what about the formal charges? Well, the oxygens have 1, 2, 3, 4, 5, 6. They have 6 valence electrons in the compound. The neutral atom has 6. So the formal charge on the oxygens are 0, but nitrogen now has 1, 2, 3, 4 valence electrons in the compound, but it has 5 valence electrons in the neutral atoms. So it has a deficiency of 1 valence electron. So the formal charge in this compound is on the nitrogen. So, so one thing I want to also say is that the formal charge on each atom has to equal to the overall charge on the whole molecule. Like for carbon dioxide, we calculated, I believe we calculated that the oxygen has a negative formal, has a positive formal charge, and the nitrogen a -1 formal charge. But we know carbon monoxide is neutral, and so if carbon has a negative formal charge, then the oxygen has to have a plus formal charge, and then we want it like this. Okay, so so that's that example. Okay, I want to do. Let's see, which one do I want to pick here? Let's do azide. So let's see. So N3 minus. Well, you know the skeleton's got to look like something. You only have this, you have the same atom, you have 3 nitrogen atoms, so they all have to be connected in a chain. So it's kind of easy to see the molecular structure. So if we put in the number of valence electrons, we'd have 5 for each nitrogen. So 3 times 5, 15. But we have a negative charge here, single negative charge, so we have to add 1 valence electron. And we end up with 16 valence electrons. So what we do, we've already put in 4, so we have to put in the remaining valence electrons. So what I would do is, since it's a symmetrical molecule, nature tends to go with symmetry. So if you put 2 here, let's just do it equally here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, let's do it like that and see what we get. And then we, of course, we know we have to have a negative charge. Now, where the negative charge is, we have to determine the formal charge once we get the Lewis structure. So this nitrogen here, how many, let's see if each atom satisfies the octet rule. Of this nitrogen here, 1, 2, 3, 4, 5, 6. Somehow we need to get 2 more electrons here. If we brought them in, that wouldn't do the trick. So we're going to bring a lone pair from this nitrogen here, and then we're going to get, so we're going to form a double bond. We still have 1 remaining lone pair. And so now this atom satisfies the octet rule. How about this nitrogen? 1, 2, 3, 4, 5, 6. This atom here satisfies. We're in trouble here still. This only has 6 valence electrons, so we have to put 2 more in. Putting 2 more from here itself won't do the trick, so we have to take them from the central nitrogen again, and then we end up with something that looks like this. And then there's a negative charge here. So now let's determine the formal charges. So in this case, 1, 2, 3, 4, 5, 6. No, we're still not. We have. Yeah, I forgot to add these here. So we still, since we brought them in from the central atom, these still have the 2 lone pairs. So the formal charge here is 1, 2, 3, 4, 5, 6. Oh, so you have 6 valence electrons, but you have 6 valence electrons, but you have in the neutral atom you have 5. So this would have a -1 charge. This one here would have 1, 2, 3, 4, 5, 6. Again, this one would have -1, 1, 2, 3, 4. This would have +1 here. So again, the formal charges have to add to get the overall charge of the molecule. All right. So this is the structure of the Lewis structure for azide. All right. So let's stop with those examples and see where we go from here. Now, which structure we want the formal charges to be distributed across the molecule so that there's not an excess of charge, of negative charge at one end of the molecule and a positive charge at the other. We want a more even distribution of electrons. And I think, let me share this problem with you. So we have all these resonance structures of carbon monoxide, and we want to find out which one is the appropriate resonance structure. So we can rule out A because carbon only has 6 valence electrons if there's a triple bond and not a lone pair. We saw before, this is the structure we determined for carbon in the previous example, where the formal charge on the carbon is -1 and the oxygen is +1. Now, if it were this is a valid structure in the fact that both atoms, carbon and oxygen, satisfy the octet rule. But the formal charge on this Lewis structure, the formal charge on the carbon here would be 1, 2, 3, 4, 5, 6. It would be -2. And then the oxygen would be +2. Theoretically, that's possible, but you have a separation of +2 and -2 across the bond distance. Okay, so you have a separation of charges. That's not as energetically favorable as a more even distribution of charges, as in example B. And then D would be worse because you would have a formal charge of -3 on the carbon and a +3 on the oxygen. So it would take a lot of energy to separate that much charge, and you would gain stability by by not building up a charge across such the bond distance. So this is where formal charges can be useful. Okay, so we're gonna stop this video here, and then we'll move on to geometry.